Some of you are new. Thank you for joining us today. Some of you are all familiar faces. Good to see you back. Glad to have a nice little crowd so we can answer some good questions today. So, again, if you have any questions after our talk today at all, please hold on to those questions. Make them good, make them juicy, and we'll answer those questions for you today. But I'm glad to hear that you all are here. Thank you to all of my friends who are watching online and who've been joining us faithfully from all around the world, every single Teen Science Cafe event that we have. So thank you for joining us. I'm super excited to hear from our scientists today. Before we get started, I just wanted to welcome up our Teen Science Cafe team to let us know a little bit more about what we're going to get into today and just start us off right. Okay, so thank you so much. Come on up, Jay, and we will get started.
Hello everyone, Callum, thank you for introducing my name. My name is Jana Lee, and I am one of the teens, part of the Teen Science Café here at the Aquarium at the Pacific. So, can we go back to the last slide, please? So, who are we? Well, we are a team of teenagers passionate about positively influencing the new generations to be involved in science. So we work with scientists to organize fun and events for you guys here in the SoCal area, or for those who are joining us online, a special welcome to you. Currently, we are doing a series regarding women who did their research in Antarctica, women in STEM, and this is really important to today's society as now we are evolving to accept a whole line of jobs as well as passionately influencing teens to be involved in this revolution. So some past lectures include Dr. Amy Moran, Antarctic Picnigonids, Dr. Margaret Amsler, Pelagic Krill, Dr. Roxanne Beltran, Weddell Seals, Dr. Kristen O'Brien, Antarctic Icefish, Dr. Sky Moret, Art Design and Environmental Data, and Dr. Chris Chang, Anti-Fees Proteins. My personal favorite was the Art Design and Environmental Data because she introduces the new topic of STEAM instead of just STEM, and that A is important and that represents art. And we will talk about it more in our presentation. So before we do anything, I would like to introduce a turn and talk. And so what happens is that you will turn to your neighbor for a few seconds and discuss the questions that I introduced to you. So what is ice? So turn to your neighbors, ready, set, go. Okay, so let's bring it in for a bit for what is ice. So can I get some volunteers to discuss what they talked about? Anyone? I'm gonna pick from the crowd. Ooh. Yes, you in the front? Yes, so water in its solid state is ice. That's correct. All right, so I'm gonna go to the next question. What do you know about glaciers? Ready, set, go. Okay, let's bring it in for a bit. What do you guys know about glaciers? Anyone have anything to say? Yes, my pal in the front. Yes, so my pal in the front just said glaciers are big and some of our water comes from the glaciers. That is correct. We'll get into more of the percentages, but glaciers store most of the fresh water that we have on Earth. And so because of climate change and that melting of that ice, it is producing more and more water, making the sea level rise. And if you think about it, fresh water and salt water, it can be diluted, right, because of these glaciers melting. So we'll talk a little bit more about that. So you're very correct. Our last and final question. What are you hoping to learn about tonight's presentations? So this can be a comment or question that you had or are thinking about right now. All right, go. Okay, guys, let's bring it in. Does anyone have any questions or comments that they would like to make at this time? Yes, you in the second row. Move? Ooh, that's a great question. So my friend just asked, how fast does a glacier move? So I want you to hold on to those questions, and if it's not answered by this presentation, we have a lovely scientist who will answer your question. All right, let's go to next slide. So before we talk about glaciers, the big picture, let's talk about what ice is. So ice is water in its solid state of matter, as we discussed in the beginning. And water typically freezes at 32 degrees Fahrenheit, 0 degrees Celsius. This is pretty normal for freshwater and a bit different than saltwater because saltwater has a lower freezing point than freshwater. This is due to dissolved solids. So that salt makes it harder for these water molecules to freeze. So introducing salt water, you need to have a higher freezing point. And another characteristic of ice is that it is less dense than water. If you think about it, when you have a cup of water, that water is free flowing and it molds to any shape you put that water in. Whereas ice, it is in this own structure and the molecules are all spaced apart. And so when you have that sitting on top of water, it's going to be less dense. So I'd like to pass it on to Amina, who will talk more about what glaciers are.
So, what are glaciers? Glaciers are essentially huge blocks of ice that are slowly moved by the force of their own weight and the force of the gravitational pull on them. Glaciers are huge masses of ice or compacted snow that will gradually move through a landmass, eroding away the earth, creating something like canyons or valleys. Example would be the Cascade Canyon in Wyoming National Park. So glaciers are extremely important. They're keystones. They provide fresh water to the animals in the ecosystem around. They reflect a lot of heat that the sun shines down on the earth. They reflect that back into space that keeps the planet cool. They also influence ocean currents. Whenever that cold glacial water melts, it'll interact with the warmer waters closer to the equator, and it will slow down the currents, and will also change the sea levels the more they melt. I'm going to introduce Madeline, who will tell you where glaciers are usually found.
Okay, so this leads us to the question, where are these giant glaciers located? So glaciers, on this map, as you can see, the blue dots represent where glaciers are. And if you're looking on the map, you can see that there's this huge section for Antarctica. And that's actually because 91% of glaciers are found in Antarctica. And after Antarctica, 8% of glaciers are found in Greenland, and Greenland is where the polar bears are. They're not located in Antarctica. So less than 0.5% of glaciers are found in North America, and actually 0.1% of those 0.5% are found in Alaska. And lastly, 0.2% of glaciers are found in Asia, and Asia also has Mount Everest, which is the highest glacier in the world. So, did you know glaciers actually hold a lot of fresh water? They hold 68.7% of the world's fresh water. And you might wonder, why are they so blue? You might think that they might be white or clear, but they're actually this bluish tint because of the weight that the snow has. It makes it very dense, so it reflects a lot of blue light. And back in the day, um, the glaciers are about 400 million years old, and in the Antarctica ice sheet, it would cause the sea levels to rise by 210 feet melted completely. But now, if all glaciers were to melt over the world, it would cause the sea level to rise by 15 stories.
So we have this some animals on the board, but we would want you guys to answer this question kind of like a churn and talk if possible. So what aquarium animals are found near and around glaciers? So for those who have had a close eye on our exhibits, let's see if you guys can find some of these animals. All right, go. All right, guys, let's kind of bring it in. So I kind of give you some hints on the screen. So does anyone want to tell me what they discussed? No? Oh, yes. Ice fish. Yes. So, well, you forgot the hint keyword aquarium animals, but yes, ice fish are some animals that are found around the Antarctica. You might want to hold that answer for the next slide. Spoiler warning. You also had yes. Yes, so some of the penguins do live in Antarctica. Not so much the ones found in the aquarium, but yes, there are penguins found in the Antarctica. So, does anyone know what gallery you might find these animals at the aquarium? What ocean? Does anyone? Well, okay, I'll just go on. It's found in the Northern Pacific Gallery here at the aquarium, and if you go look at the tropical parts of the aquarium, you might say, "Hey, what temperature might this water be?" Glaciers will not be able to form in milder temperatures like those found in the tropical, but northern Pacific, they're able to sustain colder temperatures for glaciers to form. So if you look at some of these animals, they have unique adaptations that make them able to survive in these colder environments, like our sea otters that have fur that helps them stay warm in the colder oceans.
So this is our second or third turn and talk about what animals are found near and around Antarctic glaciers. So think back to our past presentations if you were here, and if not, just any animals around the Antarctic glacier. Okay, go. Okay, so is there any volunteers? I will pick someone from the crowd if there aren't any volunteers. So, okay, yes. Yes, the killer whales are found near and around glaciers because they are adapted to colder temperature waters. Anyone else? Yes. Yes, humpback whales are found near and around glaciers as they are adapted to cold water, and they also have blubber, which helps them deal with those cold temperatures. Yes. Yes, seals are found near Antarctic glaciers, and an example of one of those seals could be the Weddell seals, which we learned about in the previous presentation. Yes. Yes, walruses are found near and around Antarctic glaciers. Okay.
I think one of my favorite things about learning about or going on this journey with everyone in our Antarctic Women in Science STEM series is we're able to learn more and more about these animals. My personal favorite is actually the ice fish right there, and ice fish have antifreeze proteins that help them survive in the colder environment without their bloods freezing over because of that icy environment. So as we go on to our presentation with our scientists, let's try to have some questions that we keep. So smooth transition. Another turn and talk. What did you learn about glaciers? Ready, go. All right, guys. Okay, let's bring it in. I'm actually gonna pick some of the people in the back, So, would you like to say anything? No? It's okay if you guys don't want to say anything, but we don't bite, I promise. Anyone else have anything? Yes. It contains the highest glacier. So like it's not the whole mountain in itself. Yeah. Anyone else? Learn anything interesting? Maybe like a percentage? Maybe found out that polar bears don't actually live in Antarctica. Yes. Yeah, so yeah. So my friend said that not all glaciers are found around oceans. Yes. So when conditions are ripe enough, glaciers will be able to, well, not form, but they've been there for millions of years, so they've stayed there. Right.
Okay, so now let's do the second part of the turn and talk. What questions do you guys have about glaciers? What unanswered questions are lingering in your mind? Okay, go. Okay, so is there any volunteers? Yes. That's a great question, and hang on to that, and we'll see if the scientist answers it. And if she does, or if she doesn't, then you could definitely always ask her after the presentation. Yes? Yes, that's a really good question. And as I said, hang on to that and wait until the scientist finishes her presentation. If she doesn't answer it, then you could always ask those questions.
It's really important that we ask these questions because an important step in science is asking questions. And Callum mentioned before in our past lectures, those questions will evolve into more and more questions. So I'm really happy that you guys are kind of thinking about these questions after you heard our presentation. So thank you for listening, and I'll pass it on to Callum, who will introduce our scientist.
Very good job, you all. Very, very good job. Very good job. Like they said, yes, all those questions are super important. I know some of you might be a little bit more shy, so you hold on to those questions in your head, but ask questions like Jay said. It's so important. You never know where those questions are going to go. Some people spend all their life asking like, why does a glacier grow like this, or why does a glacier melt like that, and why is it shaped like that, right? Simple questions, but then that turns into a whole dissertation topic where you're now a PhD student and you're trying to figure it out. That's literally how things go. So you might think that some questions are a little bit small and insignificant, but really they end up turning into something much bigger, and that's how science works. That's literally how science works. So you're never too small, too young to start asking questions. Why is it shaped like that? Or why does the water move like every little question, ask it, okay? Very good. So now I'd like to welcome Dr. Erin Pettit. She's going to tell us a little bit more about glaciers and her work surrounding glaciers and in Antarctica as well. All right, let's give her a big round of applause.
And as a treat, you get a crayon and a piece of paper. And if you can hold your eagerness, you might also get a thing of silly putty, a container of silly putty. I don't know if I have enough for all of you, but don't open it yet. Oh, that came through really loudly. Don't open it yet. Whoa. Do I need this, or can I turn this away? I think I'm on. Cool. Wow, it's bright up here. Hello, everyone. It's lovely to be here, and I really appreciate the invitation, and it was really neat to hear all of the ideas and the sharing in advance. It's really fun. For me, I come from a physics background, and so I love to think about how the physical world and the biological world all interact. So I wish I had my little, I have a wonderful little snippet of a squid swimming underneath a floating part of an ice shelf at the site that I'm going to show you about. But I didn't put it in my presentation. But I'm happy to talk about whatever I know about animals afterwards. But I will be telling you about most of the physics of how glaciers work and why they look the way they do. But first I want to start by saying that, when I was your age, giving a presentation like this, or even teaching a classroom full of students, was an absolutely terrifying idea. I was shy, I was quiet. The class I struggled with most in high school was public speaking. But now I'm talking to you today as somebody who actually loves teaching, and I love working with kids. I work with teenagers a lot. I work with undergraduate students. I work with graduate students. I work with a lot of different people and many different audiences. And I love speaking to audiences that are really engaged and wanting to ask questions and wanting to really have conversations about some of these things that I'm passionate about. And so today we're going to be talking about glaciers and climate change, and we're going to be talking about physics and art. And all of this comes together in curiosity and creativity, which are some of the elements of science as I see them, and courage, because the best science happens when you have the courage to ask those questions that as Kaylin mentioned. And it also takes courage to make a difference in the world. Right, there we go. Next slide. So science, at least the way... do I need to turn this off? What's going on? Okay, sorry about that. Science, at least the way I see it, the way I use it, the way I am a scientist, does weave together that curiosity, the creativity, and the courage. Like I said, I think it's that courage to ask questions that really is where we get the most amazing scientific discoveries. Because in order to ask those questions, in order to think about something that nobody's really thought before, you have to be willing to push yourself outside of your comfort zone. So it does take a lot of courage to step out and try to be a scientist who's open to new ideas, to thinking about the world in a different way. And sometimes I'm wrong, sometimes I'm not. Sometimes we don't know yet, you don't know yet if you're wrong until 10 years later when somebody else tries to think about the same questions. I also find that science, that most of my science anyway, and most of the most profound new ideas that I run into really take merging this scientific way of thinking with art, and it's great to see that you guys had somebody really talking about that already, with philosophy, with any of the ways of knowing about the world, indigenous knowledge. There's many different ways that we can learn about the world, and they all can be blended together to start answering our questions. We really just need to be open to new ideas. So I just put a few things up here. You know, on the left here is what ice looks like. It's really that colorful if you look at it through some polarizing lenses. So if you take, you can do this with 2 pairs of sunglasses, polarizing sunglasses, and you put a thin piece of ice between them, and you sort of move them around, you'll see colors come through on the ice. So to me, this is beautiful, but it also, I feel like this is picking up differently as I move my head. Is that okay? Okay. This is really beautiful, but it also gives me some clues as to what's really happening inside there. So you can see that there's blue more on the right side of this image, for example. And you can see that there's a bunch of linear structures in there. So these are looking in on the individual crystals of ice. Each of these is only a few millimeters across, but I can learn something from looking at the colors and the shapes and the sizes in here. Similarly, doing something different, like on the right there, I'm actually painting ice with watercolor paints. And we think of watercolor as needing water. So what happens when you put watercolor onto cold snow? In this case, the snow is at -5 degrees Fahrenheit. What happens to it? How can we learn about the ice crystals themselves from looking at how watercolor moves through it? So there's so many different ways that I use art anyway to learn about snow and ice and glaciers. Before we dive more into the amazingness of glaciers and ice sheets, I do want to share a little bit about my pathway into glaciers, because you rarely meet a kid who grows up thinking, I want to be a glaciologist. I didn't even know what a glaciologist was until I was 25. And I definitely didn't think that I could be the kind of scientist that you see pictures of in the National Geographic magazines that I devoured cover to cover every month as a kid. Remember, this was in the days before internet, and so magazines and television were kind of our key to the outside world. I grew up in Seattle, Washington, and also in Houston, Texas. We bounced back and forth. You can see a picture of me here in my high school physics class. And that's in Texas, and then the image of Mount Rainier is my tribute to Seattle because it's a big piece of why I became a glaciologist. And like I said, I was a pretty shy and awkward kid. Yeah, kind of awkward among the teenage social life. I had my friends, I did my stuff, but I loved physics and math. I also loved creative writing and art and philosophy, but I had no idea what to do with my life. I was probably a lot like many of you guys. Because I was good at math and science, though, I was encouraged to go into engineering. It's a good job, and I was told to let go of the idea of art or any of these other things being part of it. Like, go get the engineering job. Forget about art and philosophy and all of that stuff. And I knew a few family friends, parents of my friends who were engineers, so it made sense, and I did that. I went to study engineering. But looking back, I can see how I got here, even if I couldn't have predicted it then. I do remember two things in particular. There's probably more, but I'm just going to tell you a couple of them. And the first one is Mount Rainier. It's something that every Seattleite grows up with this thing on their, this giant mountain on their, on the skyline. So, but not all Seattleites become glaciologists. You guys have the ocean here. That doesn't necessarily mean you guys are all going to become oceanographers, right? Oceanography is awesome. My husband's an oceanographer, so I highly recommend it. But my point is that just having the mountain there wasn't enough to turn me into a glaciologist. But what did happen is that I was the kid sister when my brother, my older brother, and my dad went and climbed that mountain. And I was stubborn, and I was strong, and I was mad. And so I didn't get to go with them. I had to stay home. But what happened is that put it in a special place in my head and in my heart. And 10 years later, when I was in my early 20s, I called up my dad and I said, Dad, guess what? We're climbing. Did that go? There we go. Okay. I told him that we were going to climb Mount Rainier, and he did. So this was my dad, and we slept up there where that group of people is. And that's what I really remember most. More than almost anything was sleeping in a tent on the glacier with like snow gently falling on the tent, but also the booms and cracks that you could hear, the whole like these very subtle vibrations of the glacier underneath me that told me that this thing was moving. It felt like it was alive. And that really, really was something that stayed with me for many years. But in addition to Mount Rainier being prominent on the Seattle skyline, glaciers also played an outsized role in the entire landscape of the Pacific Northwest, the Seattle area, Puget Sound. Have any of you been to the Seattle area in Puget Sound? Its entire landscape, as you can see, was carved out by glaciers during the Ice Age. This was only 16,000 years ago, not that long ago. And I learned about this not in a science class. I learned about this in a history class. And my history teacher not only told me this wonderful story, told me a lot about how the whole landscape evolved, how the people lived here when they came in here, which was not too long after this. And he taught me how storytelling can really help bring something like this landscape to life. But at that point, I still thought this was history. This wasn't science. So I sort of set it aside for a while. And I ended up studying mechanical engineering. I even lived here in Southern California. I designed electric cars for a few years. And it wasn't until I was 25, like I said, or 26 or 27, I don't even remember when it was now, that I finally discovered that I could take everything I loved about engineering and apply it to how the earth works. And I could then bring back in the art and the philosophy and those ideas that I really loved. There we go. Okay. So from the physics, from the small scale tiny crystals I showed you earlier, to the dynamics of the massive Antarctic ice sheet that's shown in the background there, to the many different ecological and cultural impacts that glaciers have had on our world. Like you guys heard earlier, they provide water for ecosystems. They also they've had this story in many of our glaciated parts of the Arctic, and right here in the Pacific Northwest, they actually have a cultural history for us as well. But ice just fascinates me, and yeah, decades later, and I'm actually still not bored. I am still fascinated every day, because glaciers really, come on, there we go. Glaciers help me find the curiosity and creativity inside myself. They helped me find the courage to speak up about things that I cared about, like our impact on Earth and our changing climate. This is a glacier, the Easton Glacier on Mount Baker in Washington, that I've been visiting since 1997. And I've been there nearly every year. And we've been mapping the terminus of this glacier for most of those years. I've actually been mapping the terminus of this glacier mostly with teenagers. So people just like you, we've gone up for many years and do this. You can see a picture of them there. This sketch was done by one of those teens a number of years ago as well. And I really appreciate it, but I also can use it to teach you, to show you a little bit, as you guys heard earlier, about how glaciers form, which is from snowfall high in the mountains. So that snow compacts down. I call it the too much snow zone. It's also called the accumulation area. And that's where the ice gets formed. But then, as you learned earlier, the gravity, its own weight under the force of gravity brings it down the mountain. Along the way, it's carving out the landscape, and then it comes down to where the landscape is, where the atmosphere is warm. So this is what I call a too much sun zone, but it's also called the ablation zone, and that is where we get melt. And right here, hopefully coming up. Oh, do I go too far? This is a map showing that retreat, and we went on straight to the next one. But you can see the retreat there, and we will dive right into what happens at another terminus. So the one on Mount Baker was a land terminating terminus that turns into a river. This is the terminus of a glacier in Alaska that ends in a giant calving ice cliff. And about 15 years ago, I actually set out to study the calving of these glaciers because it's a hugely prominent piece of what we see about glaciers every day. But what I learned in going up there was that it's not the calving that's really the story in some of these glaciers in Alaska. It's the slow, imperceptible movement of this ice down valley, and then the melting of the ice at the terminus as it reaches the warm water. So the calving takes the glory in this environment. The calving events, these big, crazy calving events that all the cruise ships go look at, that kind of takes the glory. But the patterns, the story that the glacier wants to tell us, is underneath there. And we have to learn to pay attention, and that's one of the things that I want to talk to you about today, is how we make these observations, really close observations, and we get a sense of what's happening so that we can ask the questions and then ask another question and then ask another question. So beneath these ice cliffs, we had a little bit of a I think I should just go on. There was a little bit of a technical difficulty when we put it in this. So we're just going to pass on. It showed a zoom in of some little of the ice melting and little tiny bubbles coming out. But in transitioning the slide to a different, or the presentation to a different computer, that went away. So glaciers flow down through the landscape. They actually flow like silly putty. Get your silly putty out. I'm impressed that everybody kept it there didn't play with it. And you can roll it up make a little ball with it. It'll get a little bit warm in the process. How many of you remember from playing with silly putty as a kid, what happens if you pull it apart very slowly? Yeah, you get the stringiness in between. It stretches. What happens if you pull it apart quickly? Yeah. So here we go. Pulling it apart slowly, and it stretches and oozes. But if you pull it quickly, it breaks. And if you take the silly putty and you turn it into a ball, it's just fun to play with too. But in theory, if I leave that there, it's actually going to flow out and form its own little ice sheet. So you can keep that, just play with it in your hand. You can fracture it, but this is what we see here. Through some parts of the glacier, it flows. It actually, we don't think of ice as being a flowing substance, but it does deform. It's kind of like red hot iron at a blacksmith shop. Have any of you poked your head into a blacksmith shop and seen that? Where they can bend the iron and make it into anything? That's actually about what glaciers are in this line. They are the red hot iron of the landscape. So they can flow and mold their way down. And it's just when they get to the point where they're being pushed a little too fast or going over something a little too steep that they will crack. And the cracking then, I love this picture because it really shows how the fractures tell us a little bit about the story of this glacier. So it's flowing down here, but it's trying to get around this little rocky island. And as it goes around that island, it has to crack and reform its way too quickly. So the fracture patterns show us where it's moving too quickly to just flow using their ooziness. Okay, have even a close-up of this here. There we go. You can zoom in and see that fracture, these patterns of fracture. So these are the things that we start to observe in order to start to ask the questions and understand what the glacier is telling us. And if you went back to this glacier today, you would see a totally different fracture pattern because it's retreated even farther back and it's in a new stage of its life. These fractures are just one obvious way that we can look at the flow of glaciers, but they do vary quite a bit. So in these cases, we both have some nice organized patterns of fractures higher up on the glacier. This is just a zoom in of actually a section of that glacier, but they start to go chaotic sometimes as they approach the terminus. And they will change and they will vary. They have a personality, and that personality changes as the environment changes around them. So, but with this, I'm bringing back my beautiful picture of the ice crystals, because what we need to do as glaciologists in this world, we have millimeter scale patterns we're working with, and we have tens to hundreds of kilometer scale patterns and flow and questions that we're asking on the scale of the entire Antarctic continent. So we need to work between many scales, and we need to work between many spatial scales and time scales. So we need to work on the very, very long time of the Antarctic ice sheet, the 40 million years that we learned about earlier. We need to think on the time scale of seconds when a calving event is happening, and that might change the dynamics of a glacier. So we have to be able to bridge these scales, and this is one place where I see art and science coming in to help us be able to bridge these scales. Is that changing? So what I want to do right now, just really briefly, is take you through a little art exercise. That's one way that actually helps me work with my own observations. So you guys were all given a crayon and a piece of paper, and if some of you have taken, have any of you taken like an introductory drawing class? You might see some of this and it might sound familiar, but we'll come to it. So what I'm going to show you on the next slide is a photograph, and I'm going to give you just 60 seconds. Oh, I don't have my phone to get that. We'll estimate the 60 seconds. Don't worry, but this is not about creating a beautiful drawing. What I want you to do is capture as much as you can in 60 seconds. My friend who's an artist, she talks about it as she's dancing, her pencil is dancing across the landscape. So this is about super quick, big movements, not trying to get into any details, just looking for the big shapes, and see if you can capture the whole scene really quickly. And it's not, again, this isn't about creating a beautiful landscape. It's about getting yourself to see it a little bit differently. Are you ready? And go. Okay, stop. Now, just like we did earlier, I want you to actually turn and talk to your neighbor and see what you highlighted and what they highlighted, and things that you saw in this landscape that stood out to you. I'm going to turn it black so you look at your landscape. Okay, great. Okay, let's come back and we're going to do another exercise now. So flip your piece of paper over. And this time I'm going to show you the same picture, but instead of looking at the whole landscape, I want you to zoom in on one point of it, and then I want you to keep your crayon on the paper and keep your eyes on the screen, and I want you to follow lines in the landscape like an ant would be crawling across this picture. And you don't want to capture everything. You want to just stay in that one little area and just look at that one area in a lot more detail. Ready? Go. Okay, stop. So now turn to your neighbor and talk about this one. And in particular, talk about what details did you notice, but then also what was harder or easier for you with each of these two approaches. How many of you liked the first version, and how many liked the second version? You can put up the next slide. There we go. Now you can see it again if you want to point to a few things. How many of you guys liked the first one, the dancing across the landscape? That's what is called gesture drawing. How many of you liked the second one? That's called contour drawing. And if you go to the next slide, these are very common exercises that artists do. And the reason that they often do both, are there any of you that liked both equally? Couldn't decide? Yeah. Each of us has our comfort zone with how we think about the world. And some of us like to think in that big picture where we're okay brushing over some details. We just want to live in that big dancing across the landscape. And others really find our comfort zone in the details. All of that is wonderful, but the best way to approach asking questions and looking at new data and thinking about how to ask questions is to push yourself to do both, because you will see more if you push yourself to do both, even if you like one more than the other. when I do work with teens, we actually spend a lot of time doing this. So this class is the class that I teach is called, one of them is called Girls on Ice, the other one's in Girls on Icy Fjords. But the point is to get to know how the ice really lives within that landscape. So before I teach them anything about glaciers, we actually just sit and look at the landscape for 15 minutes, 20 minutes, a half an hour, depending on how much time we have. And I love seeing, these were actually a little bit more elegant sketches they did when they had an artist out there that was helping them with it. So I love showing this, but the core is both. We give them little sketchbooks so that they can keep in their pocket, so that they can be making observations all the time. Next slide. There we go. So back to here's this sketch again. And now I really want to dive into how the Antarctic is working, and in particular, one of the biggest glaciers in Antarctica called the Thwaites Glacier. It's been in the news recently. Have many of you heard it by any chance? Maybe, maybe not. It comes and goes in the news because it right now is the largest contributor to sea level rise of one single glacier. So it alone, this glacier alone, it starts in that blue section on the left there. Here I can point with the pointer. Maybe, maybe not. And goes to where that red bullseye is. And if you go to the next slide, this just shows how much mass has been lost from the whole Antarctic continent, but almost all of that is from this one part of Antarctica. So Antarctica is a little bit different than other glaciers in the sense that almost pretty much everywhere, there's a tiny places that aren't, but pretty much everywhere is this too much snow zone. Snow accumulates everywhere. Where we lose mass in Antarctica is when it is in the ocean. So when it actually gets to the ocean, we start to lose that mass. And so we can't go and measure how much is melting into the ocean very easily because it just melts straight in. So the clues that we have to look for to go find this is measured from satellites that measure gravity. So that's what gives us this picture. But when we start to dive in, we can look at it. We have to look at those fracture patterns. We have to look at the movement of the ice in order to be able to piece together the story of why we're losing all the mass right there. So go ahead to the next slide. So as scientists, we do still use little field notebooks like this to make our initial observations, but we also then extend our eyes and our ears and these observations we make with our body, but we use tools to extend those observations. So in this case, we are looking at it from a satellite, and we've sped it up. But this still is only a few years worth of time. And in this glacier, the glacier on the left, you can see it's just shedding icebergs. So the black here is ocean water, and the white is all the ice. And the main part of the continent is up there on your right. And the red line is where the ocean starts. So that's the coastline. So the rest of this is all floating ice. This ice on the right is moving at 2 kilometers a year. If anybody can figure out how many meters a day or how many feet a day that is by the end of the talk, that'd be great. The section that we have been studying is where that blue arrow is, and that's moving at about 1,000 kilometers a year. So it's about half the speed up there. And that's an example of where our site is. And in particular, we're trying to figure out if this glacier is really losing so much mass that it's contributing 1/20th of sea level rise right now, where is that happening and how's that going to change in the future? And so our camp that I was there for a month, just a little bit ago, is where that blue arrow is. And if you go to the next slide, you might see a picture of our camp. Because now this is sort of our gesture drawing, we're going to see the airborne. So we're kind of zooming down in. This is now the airplane that was taking us out to our field site. And this is that more chaotic terrain, that lower part that's moving faster. And we're starting to flow over to where the ice is moving more slowly. So everywhere here, we can see where the silly putty is cracking through all of here. but then it's not. It's flowing. It's actually stretching and oozing like that red hot lava or in a blacksmith shop. But then you can see where the flow gets punctuated by cracks along the way. So we really pay attention to these fractures because they tell us a lot of that story. Go ahead on to the next slide. So this was them dropping us off. They basically land us with enough food and tents to survive and fuel to survive for 2 months. We were only planning on being there for a month, but 2 months. And so here's our pile of stuff. And now we have to put up our camp. Go on to the next slide. This is what our camp looks like from just a little bit ways away. We have these pyramid tents that are our sleeping tents, and we usually partner up. They're really nice and luxurious. They're a bit too big even for car camping. This is like airplane camping because those tents each weigh 80 pounds. And this other bigger tent there, I'll show you an interior of that in a little bit, but that's our cooking, that's our living room and our kitchen all in that tent. Next slide. This is just a close-up showing these sleep tents, and we have to separate them out so that the snow doesn't drift in because there's storms down there, as you'll see. Go ahead to the next slide. This is what we call our science tent, and that's where we prep any instruments we're using, or we work with any electronics in there. We charge our batteries in there, and it's just a good place to go hang out on a cold day too. Go on to the next one. So this is what those cold days look like when we don't want to be outside. I did have some sounds in here, but the sounds sort of faded away in the transition of technology. So you can imagine that it's a bit tough to work here on some days, but we actually really pushed through. Some days we did stay in, but other days we were out working even in a storm. Go on to the next one. This is the inside of camp on a stormy day like that. We did a lot of laughing and telling each other stories and looking at our data and asking more questions and trying to understand the landscape around us. Here's a few more pictures of our field team. My field team this year was really fun because it was 7 women and 1 guy. Christian was lovely and really loved being. He's like, I have 7 sisters. I never had sisters before in my life, so it was great. Go on to the next slide. So we talked about this gesture drawing, dancing across the landscape, and how the satellite images give us that big picture view of what's happening. Now we're zooming in to being the little ant crawling over the landscape and really collecting the detailed data that can help bring out the story and bring out those patterns. So this is me walking across, and I walked over 200 miles across this area, not in one line, in a sort of a bunch of grids, collecting a type of data in which we use, instead of a pencil and paper, we use a radar system. So this uses radio waves, just like you listen to the radio on. They penetrate down into the ice, and they can tell us what's happening in the ice and at the bottom. Next slide. And here's an example of what this looks like. So that bottom, where it says bottom topography, you can see the ice is the darker blue, and then there's this line that divides it between the ocean water underneath. So this is already floating on the ocean and ready to become icebergs, but it's not quite there yet. And it's, despite looking really flat on the surface, this is huge topography on the underside, which really is why we need to be able to draw, we need to be able to map out those patterns as much as being able to look on the surface. This is just a little sketch from my field notebook out there. You can see, looking at the data, awesome. But these are the kinds of things that you write in when you're scribbling in there. But what this is telling us about is how the ocean is starting to carve away at the underside of the ice here. And what we want to find out is, when is it going to be so weak that it just fractures and falls apart and becomes icebergs in the ocean? So when does our silly putty go from being stretchy to finally fracturing through when it's weak enough and it's going fast enough that it goes through. Next slide. So this just to tie back to the big, so there's our dancing through the landscape, and there's our little ant crawling. I think you can go on to the next slide. And in particular, we are looking at these fractures because of those patterns, just like I said. So this just shows an example of a fracture that was hidden deep down and hadn't quite fully broken through, but now that silly putty is being stretched fast enough that it's starting to fracture all the way through. Next slide. Another one of those. It was, it's pretty profound and what's the word? It was very thought-provoking walking all of these miles because I knew that this landscape was not going to exist. This is a 1,000 square kilometer area that we're studying that is about to fall apart into 1 million icebergs. So it was a really interesting season, interesting way to interact with the ice, to be walking across it all of these miles. Go ahead. But we also looked at made these observations in other ways too. We are, we see with our eyes, and we hear with our ears, and hear with our ears, and that tells us a lot about the world around us too. And so in this case, what we're doing is setting up a seismometer to listen to the vibrations, to feel the vibrations that are left when the cracking happens. And we may not have the sound at the end of this. If they push it one more, then we might get the sound, but maybe not. No. We can also use hydrophones to listen underwater to the landscape and how it's changing. This is yet another way that we start to pull together these observations, and in this case, we're sampling the ice, doing a pretty short ice core and pulling it up. You can see it on the right. This is down like 6 or 7 meters, because we want to find out the history of the ice, what it's stored and what it wants to tell us about the history. And in this case, if you click one more time up there, what she's pointing to is an atmospheric river event that happened a couple of years ago down there. You guys, I think, have been experiencing a lot of atmospheric rivers here recently. So this is the Antarctic version of an atmospheric river frozen in and stored in that ice core. Go on to the next slide. So we can go back into the past with them, but sometimes what we want is to have the glacier tell us stories about the future. And we can look to satellite images, but in this case what we did was we built a tower. The tower's name is Bob. And the tower is going to tell us, as it goes into the future, it's going to send us information through satellite of where it is and what the weather is and a number of other things. So we can keep telling the story of this glacier as it breaks apart. At the moment, Bob has actually decided not to speak for the last few days, but he's on Twitter, but just starting. We're hoping that this is just a bug in the system that is keeping him quiet at the moment. I will send Caleb the Twitter handle when we get it going. Next. But ultimately, what I've found in all of my field work is that we can do all of these beautiful, we can take these observations, we can pay attention to what's going on around us, but there's a video up there. Is it moving? I can't tell. But ultimately, like, the best science that we get out of all of this happens when we have a good team of people working together. And that you'll get better science if your team that you're working with are happy and they work well together and they can really communicate well and you can solve problems together. So the people matter, not only because of the way sea level rise is impacting people, but the way that better science happens when you have good people doing the science. That could be you. Next. I think we're just finishing up here. So just coming back to this, to remind you that right here we have snowfall. Even where we were camped, there's still too much snow. It's all turning into ice. It's the accumulation zone of the glacier, so the equivalent of the upper part of the glacier. But then it's just getting chopped off. It's the equivalent of chopping this glacier kind of right in the middle and having it go straight into the ocean. Next. Maybe one more. There we go. So this is just a slide to kind of come back and remind us why we're looking at these glaciers, why we care about how they flow and fracture, and how they move through the environment and how they behave and what they're looking at. And that's because the sea level, even the smallest amount of sea level rise, really does matter. And this is the coast of Oregon over there on the right. The high tides are flooding the streets more and more. And this is in Florida, of course, that hurricane we had a little while ago that really caused a lot of damage. So it's really important for us to think back to why we do this. The ecosystems matter, the ocean currents depend on it, and the people will depend on it. One more slide, I think. So that being said, we need all of you guys to step in and think about what your pathway is, whether you want to become a scientist or maybe you want to become a business person and make change in other ways in our communities. But the future, who does the science, actually drives where we go with it. So getting many of you to become scientists would be awesome. And that's it. Thank you.
Thank you so much.
And I do have a little notebook for everybody, so you can collect your own, make your own observations. Do you want to? Mm-hmm. Yeah. So 5 meters a day, roughly. How many feet is that? Without using a computer or a calculator, who can do it?
Good luck.
It's like 15 feet, 15, 18 feet. Yeah, so it's a little more than 3 feet per meter. So that's like the length of this room. So if you were camped on that glacier, your tent would move that far each day.
Wow.
And I did, when I was there, ours was moving only about 3 meters a day, so like half that. And I actually did click my tent's position every single day, and you can see over a month how far my sleeping bag moved during that time.
Okay, interesting. Well, for those of you who are still watching online, I just wanted to wave goodbye so that way you know this is your time to go. But hopefully you'll visit us for the next time we have our presentation. Thank you all for coming as well. We're going to just stay a little bit behind so that way we can do some question and answers, and then we will do our activity for the day. Alrighty, well, thank you all so much.